Every road you have ever driven on, every train you have ever stepped onto, exists because somewhere an engineer decided that a mountain was not going to win. Most of the time, that decision is invisible. You board a train, you look out the window, and you never think about the rock that used to be there. But right now, in the western part of China, there's a railway under construction that is testing that idea harder than almost any project in history. If you took the distance this railway will eventually cover and laid it across a map of Europe, it would stretch from London past Berlin and almost to the edge of Poland. Except instead of flat farmland, this route climbs onto the Tibetan Plateau, an expanse so high and so vast that pilots sometimes call it the third pole, because its ice fields rival the Arctic and Antarctic in how much frozen water they hold. Building a railway across that is not really a construction project in the normal sense. It is closer to building a train line across the surface of a place that was never meant to hold one. But here is the part most people never hear about. For decades, the only way to move people and freight between Sichuan province and Tibet was a road that took over 30 hours, winding through some of the most landslide-prone terrain on the planet. Trucks carrying goods into Tibet faced routes with more active fault zones packed into a few hundred kilometers than most countries have in their entire territory. Every winter, sections of that road simply became impassable, cut off by snow, ice, or rockfall, sometimes for weeks at a time. That is the quiet cost of geography. An entire region separated from the rest of a country, not by distance on a map, but by mountains that refuse to be crossed quickly. This is where the Sichuan-Tibet Railway enters the story, a project China's engineers have been advancing since construction began in 2014. When finished, the line will connect Chengdu to Lhasa in roughly 13 hours, down from the current 34, cutting the journey by more than half. If you find videos about engineers solving problems that most of the world assumes are unsolvable, this is exactly the kind of channel for you, so hit like and subscribe so you don't miss what comes next. Why did it take until 2014 to even begin something like this? The honest answer is that nobody was avoiding the problem out of laziness. They were avoiding it because the terrain genuinely did not want to be tunneled through. The corridor between Sichuan and Tibet contains more than 200 mapped geological faults, including several classified as active seismic zones. Along sections of the planned route, elevation rises more than 3,000 meters in a surprisingly short horizontal distance, which means engineers are not just tunneling through rock, they are tunneling through rock that is under enormous, uneven pressure from every direction at once. In some proposed tunnel sections, engineers identified rock types prone to what is called rock burst, where compressed stone can fracture violently and unpredictably once it is cut into. In other sections, the opposite problem appears. Soft, high-pressure rock that slowly deforms and squeezes inward on a tunnel after it has already been dug. For most of the 20th century, these were not problems anyone had the tools to solve economically. You could build a road and accept that it would wash out every few years. You could not justify boring multi-decade tunnels through some of the most unstable geology on Earth, unless you had both the machinery and the money to do it properly. The old approach essentially was to work around the mountains rather than through them, which is why the existing road route stretches over 3,000 kilometers, even though the straight-line distance is far shorter. It was not a failure of imagination. It was an honest trade-off between what was possible and what was affordable, and for most of modern history, going around made more sense than going through. That calculus only changed once tunnel boring technology, seismic modeling, and construction financing all matured enough to make a direct route feasible, and even then, feasible did not mean easy. The pressure that changed everything. To understand what makes this railway different from ordinary rail construction, you have to understand what is happening underground, specifically inside the tunnels being bored through peaks like Sigila Mountain. The Sigila Mountain Tunnel, once finished, is expected to become the longest high-altitude railway tunnel in the world, running approximately 37.9 kilometers, with a maximum burial depth of around 1,406 meters. To put that depth in perspective, that is roughly the height of 3 Empire State Buildings stacked on top of each other, except instead of open air above you, it is solid mountain. At that depth, rock does not behave the way it does at the surface. The weight of everything above compresses it, and that stored energy has to go somewhere once a tunnel boring machine cuts a path through it. In hard, brittle rock like granite and marble, which dominate several sections of this corridor, that stored energy can release suddenly as rock burst, sometimes described by engineers as the mountain fighting back. In softer rock, the problem flips. The tunnel walls can slowly creep inward over weeks, squeezing the finished bore unless it is reinforced almost as fast as it is cut. Engineers working this corridor have had to develop what is essentially a rock-by-rock playbook, switching between drilling and blasting methods and tunnel boring machines, depending on what a given stretch of mountain is doing that particular month. Then there's heat. In some tunnel sections along this route, rock temperatures have reportedly climbed past 80 degrees Celsius, hot enough to threaten both worker safety and the machinery itself. To manage that, Project teams have had to bring in specialized cooling approaches designed specifically for high-temperature tunnel environments, treating heat management not as an afterthought, but as its own engineering discipline, running in parallel with the digging. There's a specific engineering discipline built around this exact problem, sometimes called TBM adaptability assessment, where teams essentially have to diagnose what kind of mountain they are dealing with before deciding what kind of machine to send into it. Get that diagnosis wrong, and a tunnel boring machine can become stuck or jammed inside rock that behaves nothing like what the surveys predicted, costing months of delay to free. That is part of why some stretches of this corridor rely on drilling and blasting instead of boring machines at all, a slower, more manual method, but one that gives engineers more flexibility to respond in real time when the rock does something unexpected. And this is happening inside a corridor where roughly 80% of the entire railway consists of tunnels and bridges rather than open track, according to reporting on the project. Think about what that ratio actually means. On most railways, tunnels and bridges are the exception, built only where the land genuinely forces the issue. On this one, they are the rule, and flat, ordinary track is what counts as the exception. That is the real headline of this project, even though it rarely gets said out loud. This is less a railway with some tunnels in it, and more a continuous underground and elevated structure that occasionally surfaces to become a railway. The steel challenger nobody saw coming. Tunneling through unstable rock is only half the problem, because once you are through the mountain, you still have to cross the rivers, gorges, and valleys in between, and that has produced its own quiet arms race in bridge engineering. Along this corridor, the railway is planned to cross the Yarlung-Changpo River more than a dozen times, each crossing requiring a bridge engineered for both extreme elevation and serious seismic risk. One of the standout structures is the Dadu River Grand Bridge, a crossing point so difficult that specialized heavy lift cranes were brought in specifically to place its structural sections, a job that itself took years rather than months to complete. What makes bridges like this different from a typical river crossing is the combination of factors stacking on top of each other. Thin air at altitude affecting concrete curing and equipment performance, active fault lines running directly beneath some crossing points, and valley walls steep enough that conventional construction access roads are barely possible. Every one of those bridges has to be engineered as if it might experience a significant earthquake during its operational life, because in this particular stretch of the planet, that is not a hypothetical. It is closer to an eventual certainty. This is also where the railway's broader economic role becomes visible. Once complete, officials involved with the project have indicated the line is expected to carry a substantial share of both passenger and freight traffic into the Tibet Autonomous Region, easing pressure on the older road network and reducing the isolation that harsh winters have historically imposed on communities along the route. For a region where a single blocked mountain pass can cut off supply lines for weeks, that shift is not a convenience. It is closer to infrastructure resilience in the most literal sense of the term. The world starts copying. China is far from the only country racing to build railways through terrain that used to be considered off-limits, and looking at who else is trying gives you a sense of just how difficult this category of engineering really is.
In Switzerland, the Gotthard Base Tunnel, completed in 2016 after 17 years of construction, remains the longest railway tunnel in the world at just over 57 kilometers. Though notably, it runs at a far lower maximum elevation than the tunnels being built across the Tibetan Plateau. Between France and Italy, engineers are now boring the Mont Cenis Base Tunnel, a project expected to eventually rival Gotthard in length, using tunnel boring machines the length of several football fields to cut through the Alps. In India, engineers are pushing forward with the Bonopile Railway, a line that, if completed as planned, could climb even higher in elevation than existing high-altitude Chinese lines. Passing through mountain terrain that presents many of the same seismic and altitude challenges, Japan's Seikan Tunnel, connecting the islands of Honshu and Hokkaido, remains a reference point for engineers worldwide on how to combine long-distance tunneling with harsh, unpredictable geology, even though it solved a different problem, crossing under the sea rather than through active fault zones at altitude. What ties all of these projects together is a simple, shared realization among engineers globally. The era of rooting around difficult terrain is ending, and the era of tunneling directly through it, regardless of cost or difficulty, has begun. One engineer involved in high-altitude tunneling research, when describing this shift, put it simply, the mountain used to be the boundary, and now it is just an obstacle with a known solution. China's position in this global picture is not that it invented tunnel boring technology or seismic-resistant bridge design. It is that very few countries are simultaneously tackling elevation, active faults, and extreme rock pressure across a single corridor of this length. which is exactly why engineers elsewhere are watching this specific project so closely. China's own record on high-altitude rail also plays into why this project gets so much attention internationally. The Sichuan-Tibet Railway, completed decades earlier, already holds the record for the highest railway line in the world, with over 960 kilometers of track sitting above 4,000 meters, including a tunnel that sits above 4,900 meters, higher than any other rail tunnel on the planet. Further north, the Longo-Xinjiang high-speed line runs through a tunnel above 3,600 meters. Currently, the highest elevation high-speed railway anywhere. Put together, these projects mean Chinese engineering teams already hold most of the world's altitude records for rail. And the Sichuan-Tibet line is being built by teams who, in many cases, cut their teeth on exactly those earlier projects. That accumulated experience is not a small factor. Tunneling through unstable rock at extreme altitude is not a skill you can simply hire in from a manual. It has built one project, one jammed boring machine, one redesigned support system at a time. And China's engineering institutes have now had several consecutive decades of that exact curriculum. Now here's where the science stops being theoretical. Sections of the existing Sichuan-Tibet rail corridor are already operational, giving engineers real monitored data rather than projections. The Lhasa to Nyingchi segment, spanning 435 kilometers, was opened in 2021 and has been running commercial trains at speeds up to 160 kilometers per hour ever since. Through terrain that would have been considered nearly unbuildable a generation ago, that segment functions as a live proof point for the rest of the project. A real, operating railway, carrying real passengers. Through some of the exact geological conditions engineers still have to solve on the unfinished middle section. The Chengdu to Yan segment, opened even earlier in 2018, has spent years absorbing real passenger and freight traffic, giving engineers years of operational wear data on track and structures built in seismically active terrain. Every year, those two completed sections keep running without major structural failure, is, in effect, a multi-year field test validating the underlying engineering approach before it gets applied to the far harder middle stretch between Yan and Nyingchi. That is the part that should reassure skeptics more than any press release could. This is not a paper railway or a rendering. It is a project where two of the hardest bookends are already finished, running trains and holding up. How big could this actually get?
Zoom out, and the Sichuan-Tibet Railway is not really a story about one railway. It is a preview of how China intends to physically connect its western and southwestern regions to the rest of the country over the next decade. Officials have described the completed line as eventually carrying a significant share of both passenger and freight movement into Tibet, replacing a road-dependent system that has never been reliable during winter months. At a broader level, projects like this represent a template that could be reused across other extreme terrain corridors worldwide, from the Andes to the Himalayas beyond China's own borders, wherever countries decide that a mountain range is no longer an acceptable excuse for economic isolation. If the tunneling techniques, seismic monitoring systems, and heat management methods being refined here prove durable over decades of operation, they become an exportable body of knowledge, not just a single finished railway. That is the quiet, compounding version of scale, not one project, but a methodology other engineers around the world can eventually borrow. None of this means the story is finished, or that it has been easy. The full Sichuan-Tibet Railway is not expected to be complete until around 2030, and even that date has already shifted more than once as engineers encounter conditions that were not fully mapped in advance. The middle section, from Ya'an to Ningchi, remains the hardest part of the entire project, and some individual subsections within it are not expected to open until 2027 or 2032, depending on which segment you look at. The total cost of the project has been estimated at well over 270 billion renminbi, a figure that has almost certainly grown as construction has encountered unexpected geological conditions along the way. Costs like that raise a fair question. Is a project this expensive worth it for a comparatively small population living along this specific corridor? There's also a harder, more uncomfortable limitation to acknowledge. Extreme terrain railway engineering of this caliber is not a technique every country can simply adopt, because it requires an enormous, sustained capital commitment over 10 to 20 years, the kind of patient, uninterrupted financing that many national infrastructure programs struggle to maintain across changes in government or economic conditions. That means the gap between what is technically possible and what actually gets built at scale elsewhere may remain wide for a long time, Not because the engineering knowledge won't spread, but because the financial and political will to fund multi-decade tunnel projects is much rarer than the underlying technology itself. None of this undermines what has already been achieved. It simply means the honest measure of this railway's real-world impact is still years away, tied to a completion date that keeps getting refined as the mountain reveals more of what it is hiding. Go back to that opening image. A railway stretched across a map, as long as the distance from London to the edge of Poland, except climbing onto the highest, most seismically restless plateau on the planet instead of crossing flat ground. It is easy to think of a railway as the boring part of an infrastructure story, the part that isn't a rocket launch or a chip breakthrough. But somewhere under a mountain in western China right now, engineers are proving that where a train can go is not fixed by geography anymore. It is fixed by how much pressure, heat, and uncertainty a team is willing to out-engineer one tunnel section at a time. If you enjoyed this look at how engineers are quite literally reshaping the map, hit like, subscribe, and turn on notifications so you catch the next one. Given that a railway this ambitious is still years from completion after more than a decade of work, what other massive infrastructure projects do you think are quietly running years behind schedule right now, without most people ever noticing?